Okay.
Well, good morning all. This is Dr. Keith Schubert. This is kind of the second recorded class. I forgot to bring the book last time. So I'm not requiring this book because, well, number one, it's not a regular class. It's kind of just more a bunch of impromptu lectures to help you get up to speed on some stuff that you might have seen before or might not have, but I don't want to force you to take a whole class. This book, Scientific Computing, it's by Michael Heath. It's an extremely good book. It's used pretty much everywhere as the standard textbook introduction to this. It's pretty comprehensive. It goes over every topic area you care about for an introduction thing. And it's actually fairly well written. It's got a decent amount of proofs. It's got good examples, good problems. Because it is good, it is unfortunately therefore stupidly expensive. So if you buy this new from wherever, I guess it's McGraw-Hill, if you buy it new from them, it's like 200 and something bucks. Yeah, it's like stupidly expensive. So, you know, I believe you can get it used places. I think Amazon, it's like 70 bucks or something, which is still, in my opinion, expensive for a new book. You might be able to find this somewhere else. I don't know. I can't technically say you should get an international version, but they may or may not be cheaper. This is one of those cases. This book has been out for probably 10 years. It's not like the fundamentals of this subject is changing much. So it's not like they're recovering costs. I think they're just gouging. I don't often say that, but this is one of those cases. But it is a great book. There are other good books. Sorry, it's a Mondo coffee morning. There are other great books that are out there, so you're certainly welcome to look at other stuff as it goes on. I have known from past students who have taken it and myself when I've looked back, this is one of those books I can almost always quickly find an intelligent statement on some basic things. So I find it a pretty decent coverage. Anyway, so that gives my overview of the book. Now, last time, and I'm still trying to actually convert the videos from one of my cell phones, so this is the video recorder from my house because I still haven't gotten the one from school yet. So, you know, hopefully this one will work out better. My phone one ended up in 5-minute video clips, and because it's a phone, it's got really cool advanced compression. That combination means basically no video editor I have found can work it. I can play the 5-minute video clips, but to merge them appears to be somewhere, probably one of the tasks Hercules wasn't able to finish. So I will attempt to continue to find something that can combine the videos together from my phone. But in the meantime, this will go. Prior to coming down here, I got an email from Pat that I will finally get access to the department's video camera. So hopefully next time I will have a camera available that's I know will work. Anyway, so hopefully this will go fairly decently. That's going on. All right, so that's kind of the thing on the videos. When you're going through, whether you're one of the ones who are here or whether you're somebody who's kind of watching these videos at home, there's also a bunch of lectures that I had recorded a while ago. They're on there. I think they're numbered 1 through 8 that's going on, and it starts with the basics of numerics and goes up to householder QR, I believe, that's in there. Following kind of one line of where this is going on, because it was a series of videos I was doing to help somebody understand householder, and so I was doing everything that kind of led up to it. For each of these, I'm not assigning any problems, but what I'm expecting you'll do is to take the time to try problems on your own, look at them, see if you can solve them, try to write the algorithms, and then generate some fake data on your own that seems intelligent, and from there, see if you can solve some problems. You'll find a lot of errors by trying to write your own code and seeing where it's slow, where does it have problems, can you read the data in. A lot of the stuff that comes in from practical experience. So, while I'm not grading homeworks, I really do suggest that you try them. There's also the labs online, try some of those. They'll give you some good sample problems that are out there. And there are some data sets that were associated with that and things like that. So I believe those are available. There's also a GitHub that has all the labs in it. So if you don't have that or you need to know where it's at, let me know, and I'm happy to send you a link to the GitHub area, which has, my one caution with that is, I believe I also have code that will solve it. Please don't use the code that will solve it until you've written your own code. So part of the reason I dump that in is so that, you know, if I'm at a conference or something and not easily available and you've got something, you want to look at it, you'll have something you can base it off of. But it also has the LaTeX source to generate the overall manual. The manual is designed that you can edit the manual yourself, and then when you edit it yourself, you end up kind of writing a book of how to solve these kind of, what I think are kind of archetypal problems. And so I'm hoping that'll become a good reference for you in the future as well. It also, I believe, has some data that you can use for some of the problems that you don't have to re-enter. So hopefully that gives good background stuff. Now, last week we were talking about how to find the zeros, which I argued at the time was one of the basic problems that can pretty much solve anything. So now we're going to take a look at another one of those kind of basic problems that can pretty much solve anything. We're going to go through a series of these ones. And as I mentioned last time, this is really taking a look at fundamental problems. I could build an entire house with a hammer if I really wanted to. There's a lot of jobs where it wouldn't be the best tool to use, but I could force it to do it. You know, I could pick up a wrench and again do the same thing. I can pound things with the wrench, even though that's stupid, right? But I could do it. And you can, if you get a big enough screwdriver, you can pound with the screwdriver and screw it. So there's a lot of basic tools that are out there. There are things that it fits well for and things it doesn't. So what you want to do with each one of these is see, how do I convert into this? When does it work well? When does it not work well? And then pick the right tool for the job. But realize, if you're limited with what you got, you can always adapt. And that idea of adapting and flexibility is really fundamental to the engineering way. Because not that you're ever going to want to maybe force one of these into that situation, but you might be in a spot where you have to force something else. So if you watch on the video and I'm kind of looking off to the side, that's because my audience is sitting off to the side here. So, all right, let's get into what this kind of fundamental thing is. So this one carries on the matrix formulation that's going on. So when we're dealing with matrix formulation, and I'm going to try to be a little bit cautious not to get into some of the stuff that's covered in the videos that's already online. One of the basic things that we want to do is see, you know, how do we get matrix equations and what does it matter? So I'm going to broach a little bit into one of the homeworks, or sorry, one of the lab assignments that's in there, because the purpose of one of those labs is actually to show you a good way that you can generalize equations. So that one is a truss problem that's going on, and I'm not going to solve the whole thing. But it's a problem that's like this. It goes on. And I think there's like a force here. Something like that. Anyway, I don't remember how I labeled these. I go like A, B, C, D, E, something like that. Real quick, some notation. This is a truss, okay? You might have done some basic stuff in your freshman engineering course or something on trusses. The important things about trusses is that a true truss, what makes them strong is that there is guaranteed no shear or moments that moves through this structure. So when you take a look at any type of a physical structure you build, you've got tension and compression, which goes right down the main axis. Most materials are ridiculously strong in those. And you can find some materials are better in tension, some that are better in compression. I say ridiculously strong compared to if I've got shear, which is like a tick and I'm trying to break it off. This is like what scissors do, right? One side's going up, the other's going down. There's no twist to it, it's just you're trying to cut or separate them. And a moment is I'm bending the thing that's going on. Most structures are really weak against shear and moments, but they're really strong, and you can find really strong materials for tension and compression, one of which is, for instance, decent metals like steel or things of that sort. So if I can force something that I'm guaranteed never to get a shear or a moment, the structure will be much stronger. The way we do that is we just don't allow moments to be carried. And you can do that very easily by at the joints up here. And I'm going to oversimplify the picture, but what I do is I just make a series of connections that each one overlapping has, it's kind of like a washer type symbol. Now you could obviously do it different. I'm not saying this is the best way to do it, but it's the easiest one for me to draw. Right? So each one kind of has this shape that's coming in, and I can pin them, and I just overlap and I put a pin there. Now that means between these ones, the only way they can't support a moment because they'll just rotate. So moments and shears cannot be carried by this type of a structure because pinning the joints prevents them from ever being able to convey them. It'll just rotate if that's ever the case, and then the shear or moment will go away because it'll go to equilibrium where there's no longer a shear or a moment. So by pinning all the joints that's going in, right, I've removed that whole problem. Now the members can only be in tension or compression. This is kind of the fundamental thing. So if you ever notice railroad bridges and everything else, right, they're really stupidly strong because they don't have to worry about those other ones. Now if somebody comes in and like bolts these in multiple other spots around, they'll actually destroy this property. They could actually weaken the bridge, this sounds silly, by putting more bolts in and securing it more. You don't want it secured more here. You want a good strong bolt that's just going to hold it together, but allow it to theoretically rotate. That avoids the whole problem on this. Now, once that's done, because this is the case, now if I use triangles, triangles can't change their shape. But the joints can't carry moments. So now I've got something that's fixed that won't carry moments. So I've got now the best of both worlds. So I can have a predefined angle that I know. So I can have this theta and this theta I can label as B, A, C, right? Just going through, just like you would typically do in any other situation to let you know. Now I can go for each one of these and carry it in. Now, what happens for all these situations, if I come in and I make my axes, say I make this my Y direction, I make this my X direction, I can now resolve forces in every single one of these that's either in the X or the Y direction. What's going on? So I can take a look in each one of these. I'm going to have to worry about tension and compression only. Right? Now the difference between tension and compression is sign. Right? So if I'm in tension, I'm pulling apart. If I'm in compression, I'm squeezing. So you can write it either way, whether you're doing tension or compression, and then whichever way the sign comes out. If it comes out the same, you guess correctly. If it comes out negative, you guess wrong, but who cares? It still works. So we don't have to worry about that. Now, the way in which we can now handle these is if I make a matrix that I want to describe this as, I can take A, V, and I write all of my directions down. So all I have to do for each one of these is say, this is where it's coming from, this is where it's going to. I'm going to just worry about X for the moment that's going on, because you do the same thing for Y. So you just have two of these. Then where do you interleave them, whatever, that's kind of your choice when you go into it. So, but if I want to have this one that's going from, let's say, A to C, it's purely in the X direction. So you're going to get 100% of whatever force is carried. So imagine I'm talking, there's some force in this member, right? It could be tension or compression. But right, I've got a force that's between A and C. The fraction of that force that's going to be carried by that particular member between there is 1. Right? So this matrix, I'm going to have a vector of forces that will multiply the matrix. Right? And so for each one of these, all I have to do is, between A and C, there's 1 that's going on. Right? So I can look at these as it's going, and I can I'm just dealing with the first row right here that's going on between each one of these. I'm just talking about how are each of the ones connected. A to B, well, that's connected. This, the amount in the x direction is cosine of this theta times that force. So from A to B, I've got cosine theta of BAC. A to A, there's nothing there. I can just, this is in the x direction. All I'm doing, this is just the sum of forces. Right? Sum of forces in the x direction on this particular node that's going on. And I can walk through. How about on B? Sum of forces x direction, right? Well, I've got this one, and it's pulling to the left. So what was positive here will be negative here because it's pulling in the opposite direction. So on here, I would have going from A to B, I would have minus the cosine. Now, I'm going to introduce an abbreviation. We standardly just say cosine of theta is just, I'll simplify it here to cosine theta, but eventually we just call it C. Because we just do it so much, right? And sine just becomes S. Now, part of this is laziness, but part of this is practicality. When you have a large matrix, we usually try to design these so the angles are the same, right? So it's just repeated. If I'm trying to fill in a large table and I want to fit on a page so you can see it easily, if I use C and S, I've reduced a lot of letters. It's very quick and easy for you to notice it. If I have different ones, I can call it C1, C2, right? It's much quicker to see C1 than to actually, there's a lot of wasted information here. What do you really care about? Well, you care about this, the cosine, and you care about that, which specifies which angle it is. This information here is irrelevant. Okay? So if I were to shorten, BAC to just 1, then I just have C1. I mean, which one honestly is easier, right? This is smaller, so I can fit more information on a page, and you can get to what you care about faster. So this is just kind of my arguments on why this is a better way to go. But it's easy enough to do. So this one's going in the backwards direction, so I do minus. The other ones are going to be plus. From B to D, I have a 1. Between B and D, I have a 1. And from this B to C, assuming I picked the same area that's going on, right? I can either take this as this is the same theta as it's equal, or I can, take a look if I want to preserve the area. I can take the same, and call this theta 2, where theta 2 or theta B, C, E, right? If I pick it as theta 2, right, you can relate that's, pi minus theta 1 or whatever you want. But I'm not going to worry about that as much here. B to C, I can just put in that this is the cosine of my theta 2. However you label them as you're going on. If I decide that I want to make this equilateral and I choose to call this theta 1, right, then I can take my theta 1 as it goes, but I'd have to put the minus sign on. Well, actually, for this side it minus, for this one stays plus. So however you choose to go about playing that one. From B to B, there's nothing, and obviously there's no connection from this one to E. And you just walk through each one and do it. It's very simple to build up the connection matrix. Then all I need, I've got all the forces in here. So this matrix that ends up resulting, I can call this thing script EA. Right? So I have my script EA times a vector of what's the forces in each one of these. And what that's going to tell you is that's going to be equal to the net, maybe I'll call this one script EF. Right, because this is the forces in the members. And then there's a net force. I might use capital F's here because I use capital F here. Right? That's the net force that's being applied on here. Well, here there is an unbalanced, so it's the weight of the car or train car or whatever it is at this node. Right? So right at this point, I've got a force that's, together this with that will become equilibrium, but this one is a net force on it, whereas here, there's no outside force. So all I've got is the outside forces, which will include, right, these ones impose forces. This imposes in the X and the Y. This one only imposes in the Y, because it stops you from falling into the earth, but the wheels let you roll. Right? So your X can move, but your Y can't. So this one will impose a constraint in the Y direction, balancing out any forces that go on by whatever the weight of the whole structure is. Right? So that'll become an outside force on here, but in the X direction won't. The reason why you do this is thermal expansion and things of that sort. Right? In the summer when it heats up, if you don't do this, it will bend and warp and all kinds of stuff. Right? I don't want to get too much because that's mechanical engineering junk. Right? But what you've got in here is a way to relate the external forces to the forces in the members. Now, at this point, I can get these pretty easily. Right? This, we just showed how to get it, so I have a bunch of unknowns. I'd like to know what are the forces going through here, because once you know what the forces going through here are, you can correctly select the particular beam cross-section you want. Right? Do I want I-beam? Do I want channel beam? Do I want to make it a steel? What type of steel? Right? All these type of questions I can now solve by knowing what the forces are inside my structure. I can now size it correctly. So I just put the worst loads I'd ever expect on here, solve the stupid thing, find out what the internal forces are, and away we go. Now, this, when we've gone in, I kind of pick, my external forces, my internal forces, and my coefficient matrix, but this looks just like AX equals B. One of the standard equations you're always trying to solve, right? There's a bunch of knowns, there's some type of a matrix that describes the system, and some unknowns that are multiplying that matrix, and you want to find out what those are. Now, I did this for a bridge, but realize I could have done an electrical circuit. Now, since this is in, I'm in ECE and stuff like that, I deliberately didn't pick an electrical circuit because I think you probably get that, beyond all belief. The ability to do Ohm's law, V equals IR, or, deal with all kinds of other different, basic circuit analysis stuff. Here I want to get a Thevenin equivalent, I want to do whatever, right? I'm going to do node analysis, mesh analysis, loop analysis, right? You do all this fun stuff to get different, set up the equations, but again, now you're going to find this between, V equals IR type of stuff, where I'm going to write it in the reverse direction. It doesn't actually matter in the scalars, but it works much better on others. I've got my EMFs, I've got my resistances, potentially complex to handle inductance and capacitance, and then I've got the currents flowing through the system. So again, you've got B equals AX equals B. Right? So Ohm's law falls into the same thing. So electric circuits fall into this. Turns out that I did this for here. I could have these connections instead of being solid beams. What if I made the connections a bunch of springs? The nodes have masses on them, and there's some type of a damping force between them. Right? This is the famous spring mass damper type of stuff, and physics does this ad infinitum. You could do this in a rotational setting, and you get pendulums. Right? But all these things end up generating these type of equations. So this is a little bit of a long-winded introduction on my part, just to show you that this really solves a huge number of equations and a huge number of problems that's going on. It solves pretty much any type of a static system, or something that goes to any type of a nice steady state, simple harmonic motions, things of that sort, can directly fall into this. And by introducing like Laplace transform, I can take anything that's in an ordinary differential equation and turn it into this form as well. So if we're okay with this, I'd like to just briefly give the explanation of that, because that will give me one more test case for why ax equals b is really fundamental that's going on to them. So, anyway, you get to solve this truss problem, you get to write the code for it, stuff like that. So this will hopefully set you up nicely for that. All right, imagine I've got some type of an equation that's out here, x dot equals ax. I'm just going to do a scalar for simplicity, and then I'll show you how we can work these out. As I mentioned last time we talked about how this gets into why this is such a fundamental problem, and the expansion using Fourier and all that is so important because we were dealing with complex exponentials, and that's kind of the fixed point in the function space for calculus. Well, that introduces the idea that these transforms, Fourier, Laplace, are fundamental. I'm going to do Laplace because it's, technically they're both equally general in their usage somewhat. There are a couple cases where things will work better in Laplace because when you do Fourier, this is the complex plane, imaginary, real, technically you're coming right up this axis, circling out to infinity, and you're calculating the residual of this left half of the plane to come back. If you've got a pole, right, the zero of the denominator of your function on this axis, I can theoretically take this and I can kind of loop around it. Right? But if I get multiple, this becomes actually really pretty ugly. And what happens if I have an unstable pole or something that's going on somewhere but I want to account? So what I can do at that point is, if I have the Laplace, I can shift the axis I'm integrating on. And that's all you're doing with Laplace when you're introducing the complex one. Instead of going up and down the x equals 0 axis, you're picking an offset on which side. So it just allows you to choose the line that you get to integrate up. And I can pick a line that doesn't hit anything. And therefore that'll simplify my life. And if you end up liking to just go right up the axis, it's a subcase. Now it turns out that you can handle pretty much everything. There are some cases where you can't, but you can handle an awful lot this way. It's just not always as nice and pretty. So I am therefore partial to doing Laplace transform. It's kind of a long-winded thing of why I'm going to write the Laplace variable s instead of omega. That's going on j omega. When you take this, what's the Laplace transform of this equation? So kind of my test to see where everybody's at. I'm not necessarily expecting you to know it, but it just lets me know what detail level. Now let's me sip some coffee. So we want to think about our transform pairs. X of t by the Laplace transform goes to capital X of s, right? It's going in. So right, and then you have the initial condition area that's going on. I might have to do the minus x of 0, but I'm not going to worry about that's to match the boundary condition. I'm not sweating that one as much because we're going to worry about getting those coefficients right later. So I'm just going to worry about the basic form of the equation that goes on here. This is what's so neat. If I take the Laplace transform that's coming in, right? A stays A, X goes to capital X. I'm not going to worry about writing the parentheses S just like I didn't write the parentheses T. But this side goes to S, capital X, and X is what I want to know. So if I take this to the other side, I've got S minus A times capital X equals 0. So if you notice, this is some relational matrix A, this is my unknowns, and this is a vector something. This is the homogeneous. If I had put in the minus part over there, right? I would have the minus part here, and I'd take it to the other side, and I'd have the inhomogeneous, right? Or particular solution that's going on. So if I had included the minus my x of 0 thing, I could have taken on that plus x of 0. And so then my b would be non-zero. But what do I care whether my b is 0 or not 0? It's just a choice of b. So that's why I'm saying I'm not sweating this right here. Because the particular solution doesn't really give you an awful lot more than the homogeneous did. I mean, transients and all that stuff. But if you look at it, by using the Laplace transform, I can take something that was most definitely not in that form, and I can get it into this standard form. Now, this is just for scalars, so we go, yeah, okay, who cares, whoop-de-doo. Well, the neat thing is, if I can show that I can get a matrix form like this, the rest of it will follow through, and these will just be replaced by true matrices and vectors. So imagine I had a higher order equation. X double dot equals a x dot plus bx. Again, I'm just going to worry about homogeneous. I don't have no forcing function on here or anything of that sort. But really, all that's going to do is just going to change this. That's the external conditions. And remember, that's the same thing on the bridge. What was it at this particular time 0 and what's being imposed on your boundaries after time 0. So all this, particulars. So if I look at this situation, I can take this and I can bring it over, but, and it will simplify up to some extent. Because if I take the Laplace transform here, right, I'll get s squared capital X equals a s x plus bx. And you go, okay, great, right? And I can take this and I can still redo it. But I'm going to submit to you that I can even go simpler than this. Because this right here is still a big individual equation that's going on. If I wanted to add in a second differential equation, I'd have to have 2 and solve them. But this is a second order one, and the solution to this is what? X dot equals ax. X has to look like, right, e to the at, right? With some coefficient in front of it and some constant, which you find out by the boundary condition. But we find out that your x is e to the at. How about x over here? Well, I can have the e to the at type of stuff. I can have cosine or sine. That's going on. But, and you're probably thinking, well, there's also the t e to the at. The whole trick with the t e to the at is going to turn out to be a special case off of this one, which is what we call a Jordan vector. It's what happens when the eigenvalues don't go. But again, it's when does that happen when you're looking at this? It's kind of a little bit funky to see. When you look at it in the matrix form, it's clear. And it becomes a really easy, obvious extension of what's going on. So I submit it's just kind of easy to remember. It's still a basis function off this, and that's just a degenerate case. Right? So there's potentially a t in front of it. But cosine and sine are related to this. They're just the complex. Right? Because these ones have imaginary, so it's e to the I something t, right? Depending on whatever you have inside here. But if you take e to the I theta, it's cosine theta plus I sine theta. So because of this, you can rewrite cosine or sine in terms of this. Is everybody familiar with Euler's? So real quick, like if I want to write cosine here that goes on, this is probably one of the great achievements of modern math. And if you ever take complex exponentials, this is why it works so much. This is kind of a carry out of why this is such an E is to something as such an essential program. Imagine I did e to the minus I theta. I just took theta rotating in the opposite direction. Well, if I put in, that would be cosine of minus theta plus I sine of minus theta. Now, cosine is even. So cosine of minus theta is the same as cosine of theta. And sine of minus theta is odd. That's the same as minus sine of theta. So now I've got two equations, two different ones. I can get rid of one. So imagine I took and I added these together, I get rid of the sign. So I would find out that e to the I theta plus e to the minus I theta is equal to 2 cosine theta. I now divide by 2, and there you go. That is cosine of theta in terms of complex exponentials. In this case, purely imaginary ones, but you know, same idea. This is actually why capacitors and inductors get sinusoidal response that's going on when they just do normal damping areas that go off. You're just dealing with purely imaginary. It's what their reactances are. So because of that, going in the imaginary direction, of course it's going to induce this. So this is kind of a neat relation. I could do the same thing with sine if I just subtracted. If I did minus, I'd get minus plus. These ones would add. These ones would cancel. And I would get this minus that divided by 2i. And that would give me sine. So I can rewrite sine and cosine purely in terms of exponentials. At which point, you know, now if theta was an omega t, it would look just in the same form. So just replace theta by omega t and you're done. Okay, does that make sense? So given that that's going on, right, when you do write it into this form, the s squared and all that is going to naturally kind of want to give you, if you look at the s minus a, that's e to the at, if you look at it as a Laplace transform pair. If you look at the s squareds with something, you naturally get these sines and cosines, potentially with some exponentials in them. If you just treat them as complex exponentials, it's a simpler table of Laplace transforms to deal with. So it's a little bit nicer. And simpler is really important to us because we want to teach a computer to do this. And computers are stupid. Right? So we don't want computers to memorize huge chunks of things or whatever else. We want one simple thing that will work no matter what. Because now you can go on. So I'd like to be able to rewrite this problem into a simpler form so it looks like it. Well, imagine I took this original equation. So this would work, but it would be nice to get simpler. Right? Imagine I took this and I defined x dot to be equal to z. Just make a new variable. I'm allowed to do that, perfectly legal. That means z dot is equal to x double dot that's going on. So now I've got an equation that's going on here. Right? So I can take this and say, well, x dot equals z. There's one equation. And I've got my x double dot, which is z dot. I'm just sticking this off to the side just so we remember. But that means I know what that is. X double dot is this. A x dot, but x dot is z. So it's az plus bx. So just taking that equation, which we just note is equal here, and noting that x dot is z, I've got my two equations here. Now, I can write this in a nice form. If I claim a variable x, z, and I make a vector out of it, and I dot it, I've got x, z on this side. X multiplies the first column, z multiplies the second column. Well, this first equation is no x, 1z. And the second equation is b of the x's, so b x's and a of the z's. So this equation is this equation. So now I've shown I can take a second order equation and I can turn it. This is called companion form. There's a couple different versions. If you flip the order of x and z, it'll rotate the matrix, right? Flipping the columns and stuff like that. So sometimes you'll see these ones flipped in different directions, depending on did they put z on top or x on top. This is actually largely a function of the school that you learned this at, because the first time I dealt with all this type of stuff was in Southern California, because that's where my degrees are from. What's going on? And this was, they always did UCLA, where I got my master's, Santa Barbara, right? Redlands, where I did my undergrad. Everybody always wrote them in this form where x was first. So therefore I write them in that form where x is first. A lot of East Coast schools I've noticed write with z first. And if you do it that way, what you'll notice is if z is first and z is on top here, and this a goes up to this corner. So you'll see them written in different orders. So if you see them written in funny orders or things like that, don't get freaked out. More than likely, all they did is they just flipped the order of the vectors that are in there. That's, I just mentioned that because I've known people go in there like, oh my gosh, there's so many companion forms. No, all they've done is they permuted the vector, right? And there's nothing magic to it. So realize I did this for a second order, but I could have done it for a third. Just like I introduced, z for x dot, I could have introduced some other, whatever, z2 for x double dot and done a third order equation. So I could have done this as big as I wanted. So you can get as high an order as you would like, and it goes in. And this is nicely in the form of a vector dotted equals a matrix times the vector, which brings you back into that form, x dot equals ax. Right? Where now I'm dealing with vectors and matrices. It's no big deal. And the second I do that, now I've got it in that form. Now these are just matrices coming down, but who cares? So again, I come down to here, where this is going to be my system matrix, this is my vector of unknowns, and this is all those external constraints, the particular part of the solution, or make it equal to 0, get the homogeneous part. But who cares? Now I'm handling any differential equation you happen to want. Now the other nice thing about this form is, what if in addition to this one I've got, say I came through and I put 1s here and I had some separate equation. I now had a 2, which was x double dot 2, a second set of equations that was some a2, a different coefficient. Right? I could have, these could be two completely separate things describing different areas of the system that's going on. This could be linear motion and this could be the rotations that's going in. Well, in the matrix form, all it has to do is just stack them with the relative variables. So I can take these and I can combine them nicely in the matrix form, which is really easy to do, and I just look at which variables overlap. Whereas if you do them separately, you kind of have to handle that manually. Right? Now sometimes that is the right way to do it, to handle them separately because you break the problem down. But at least conceptually you should understand I can stack them into a matrix. And now I've systematized a way that I can deal with them separately, because I can now go in and wherever I can block partition the matrix. Block partitioning the matrix is breaking down and solving the problem separately. So if they're truly independent, then they're going to end up with all the cross parts of the matrix being 0. Right? And if they're not independent, there'll be stuff in those. And so those non-zero parts in there will have to be handled when you start to try to divide the problem up. This becomes really important for us when you do imaging and you're trying to solve imaging the brain or whatever using protons. We want to partition the problems to be able to handle it. Well, it's the same exact thing as somebody's going to do when they're trying to solve a differential equation. And this could be a spring mass damper, this could be an electrical circuit, this could be a proton traveling through a brain, I don't care what. So I'm hoping at this point I've given enough to indicate to you I can solve a disgustingly huge amount of problems. Right? I can handle all your standard algebra equations, and I can handle your differential equations, all ordinary differential equations, even a slight extension of from your ODEs. I can actually go to what are called DAEs, differential algebraic equations. It is a slight extension of these. I don't want to get too much into the weeds on this because I'm just giving an overview. But, you know, all these come directly into this. And then there are simple extensions of this that go to PDEs. You know, there are some kind of ugly things that can happen in PDEs too, but, you know, I don't want to completely gloss over it. But there are ways to handle, you know, some important PDE problems in a similar looking way. Right? And there are, you know, nice ways we can handle that. It typically takes entire courses to go into the like spectral methods and things of this sort. But again, this is a first course, so I don't want to get too far into the weeds. All right. Do we feel comfortable with the motivation? We can write a disgustingly huge number of problems. And part of why I went through this in this way is I want you to be able to write the problems. And, knowing that something can be done is good. Being able to do it is better. Right? If you understand, at least to me, what's always been helpful is if I know what's the idea behind the problem, I can usually figure it out. And I typically find if I don't know how this problem would be used or what I would do to solve it, I mean, honestly, to me at least, I don't think I know what I'm doing. So what I'm trying to do here is just give you enough that I think you can solve some simple problems, and if you needed to, you can pound into more difficult. And that's where you would try them. So there's one part which is set up the second half solution. Most of what we typically do in this type of an area is how do we solve it once you're given this. Okay. So I'm now going to move into what's really what I wanted to talk about today. Everything up to here has been kind of lead up. But I think it's important lead up that's often neglected. And as much as I do happen to like this book, I don't think this is the one thing most people in this area don't do a lot of, is they don't do a lot of lead up. There are some books that do. They think it's really boring, kind of a tough trade-off. Anyway, so let's get into how do we solve these. I'm going to start like most people do by taking a simple subcase. And we're going to go from that simple subcase, and then we're going to try to solve up larger cases from it. And it'll turn out that this simple subcase will become a fundamental portion of any larger solution that's going on. So I'm going to start, we've said we have some equation that looks like this. But I'm going to assume that I have a triangular matrix, which means A kind of looks like this. If you're to look at it, the boxed in part here is non-zero, and it's 0 below. So that's what we mean by triangular matrices. So this is the main diagonal that's going on. Now, there'll be some things about this, right? I'm going to be able to, most of my techniques after this are going to be trying to force things to look like this, right? But then what I want to show you is that this works really nicely, but there are some dangers to it. And where those dangers come in will actually help us out to figure out what's going on. So if we assume that we've got something in this form, I'm going to write it as a small 2x2. And if we do the 2x2 and we show how to handle the steps of the 2x2, I submit to you the rest of it is pretty straightforward. Because you could take any little subsection and work off it. So imagine that I've got, you know, B1, B2, A1, A2, A3. I'm not going to do the, maybe I should. It's a lot easier to just do 1, 2, 3 here, but if I do it this way, you'll be able to extend it from the sub-matrices. It's always row column that's going in. Right? And then this is times our x, which will be x1, x2. If you think about any one of these, this is the b value goes first and the x value second. So A11 is the value that connects x1 to b1. A12 connects x2 to b1. So you think the subscripts, and this is why we always want RC, it's not as good to do CR. While theoretically it's just a naming convention, the way we write our equations left to right is going to force it. This one is this first one. This two is the first one that's going on. And then this, right, is the second where they're carrying in. So if you did it in the reverse order, it'd be a little more convoluted. I have to rewrite that. But I do think it is important. To me, it sounds strange, but when I was learning this, the nomenclature always just annoyed me until I figured out why. And I've often been told I'm a little too anal on these type of things. But I think if you understand why something works, you can remember it. And I'm dyslexic, so memorization is not my friend. But understanding is. All right. So if I've got this situation that's on here, how can I solve the equation? Well, normally when you're dealing with problems where there's two simultaneous equations, you got to do something to remove a variable and whatever else, but I've already got one where the variable's removed. If you look at this last line says B2 is equal to A22 X2. So I know what X2 has to be because it's got to match this equation, the bottom row. So that means that since B2 is equal to A22 X2, I can rewrite this for X2. X2 has to be B2 divided by A22, provided that's not 0. If it's equal to 0, I've got a separate area, but that means that I have no way to solve for X2. So things will kind of get ugly at that point. But now I know what X2 is equal to. Now this could have been a huge matrix, right? Even if there was more stuff going up here, right, that's going on, I could still start in this lower corner where I just have one value, right, and I'm only dealing with one variable. Now, if I look at the second equation now, I now know what X2 is. So when I write that second equation is B1 is equal to A1 1x1 plus A12 x2. And this kind of makes it nice again. You notice 1 all on the left, the 1's match, the 2's match. So if you think about it, this gives you a quick way when you're writing these down to check that you didn't make a mistake. And in computer programming, that becomes really helpful because those indices become a pain.